In this video, we're going to look at systems of equations that give us a different number of solutions. The ones that we just worked our way through each had a unique solution. 1 point of intersection if we looked at the graph. Now, when we are looking at a system like this one here, also I went ahead and made it to where we don't have any ones in front of the x's or y's so that we can see an example of what we have to do if we have to change both equations. Now, it doesn't matter whether we decide to eliminate the x's or eliminate the y's. And you can use substitution here, but most students really prefer elimination unless they're told they have to do the other. So that's what I'll default to from here on out. But again, if both have the same number of steps, I just work with the x's personally because they're out in front and I don't have to hop to the middle with my i's. I have a 4 in front of one and a 6 in front of the other. And so if I'm looking for the smallest pair of opposites that I can create out of 4 and 6, then I can make 12 and negative 12. Now, if you want to take the top times 6 and the bottom times 4 and one positive and one negative, that's fine too. There's not a rule that you have to use the smallest number. But anytime I can use smaller numbers over larger, that's my personal preference. So if I multiply both sides of the top equation times 3, I have a positive 12x and a negative 18y equals 21. So if I chose to make the top equation start with a 12x, that means the bottom equation needs to have a negative 12x. So positive 6 means I need a negative 2 to make negative 12x. I want them to have opposite signs. Again, there's no rule that says the top one has to be positive 12 and the bottom one negative. I could make the top one negative if I'd like and the bottom one positive. From here, when I go to add them together, my x's go away like I wanted, but notice what else happens. Okay. When I tried to make my x's go away, so did the y's. Now, a lot of students will just kind of leave a hanging empty space over here on this side of the equal sign. I still have to put something here to represent what remains. And if everything canceled out, both x's and the y's, then I'm still left with 0. On the right, I'm left with positive 1. If when I go approach a problem and I'm trying to get rid of x's or y's and both variables go away, then I have to read the statement that remains to figure out which of my other special cases I have. I'm either in the case where I have no solution or I have an infinite number of solutions. And so when I look at the statement 0 equals 1, I say, well, that is not true ever, no matter what. And so this is where, and if this would have happened in other chapters as well, this is where we would have stopped and said no solution. You can either say no solution in words, you can give me the empty set symbol, or when we're dealing with systems, you can tell me the system is inconsistent. Okay, any of these three, you don't have to write all of them, okay, but any of those three statements would be true and correct. And that's what you need to tell me. So doing the same kind of thing over here, let's stick with x's again. And let's turn them into opposites. So think of what you could multiply the top equation times and then the bottom equation times to create opposites like we did over here. Okay, pause the video, do that, and then put your new pieces together, and it's going to look similar but still different from the situation we have here. So pause it and then come back when you're ready. Okay, so this time when we create opposites on the x's, the y's go away as well, just like they did on the left example. But on the right side, I also get 0. When I read this statement over here was false. Okay, that's not true ever. 0 equals 1, 9 equals 12, 4 equals 7. Okay, those are not true statements. 0 equals 0 is true, and if we use substitution, sometimes we get 8 equals 8, or 10 equals 10, or 1 equals 1. But whatever it is, has no x's, it has no y's, and just has two numbers that are equal to each other as a true statement. Okay. That's how we know that we have an infinite number of solutions, that we have a dependent system. In the case in this section when there's only two variables and we're looking at straight lines on the chalkboard, then that means they're the same line. Now, a lot of students will just write here and tell me it's dependent, or they'll tell me infinite solutions, infinite number of solutions. And while that's true, that's not a complete answer. If there are any solutions at all, we need to write down what they are. Now, last semester in intermediate algebra, I let us kind of weenie our way out and say, hey, I'm just going to circle one of those equations and call it good. I told you that with a disclaimer that this semester we are going to get to go farther and be more specific and write down that solution set. So from here, once I have found out that, oh, there's a whole bunch of solutions here, I need to tell the reader what they are. And when I say tell them what they are, I'm not going to say, well, the solution is 1, 5, and 2, negative 3, and 14, negative 7, because I can't list all of them. There's way too many. So I'll pick one of the equations, and if you like the bottom one better, that's fine. I just picked the top because it was the first one I looked at. You can solve it either for x or for y. It doesn't matter. So maybe I want to solve this one for x. Also, your author will ask you specifically to solve for a certain variable. Okay, I don't care. If it says solve for x and you want to solve for y, that's fine, and vice versa. If we divide all three terms by 6, we get 3 halves minus 2y. We know that if we have solutions to our system, we have to write them as ordered pairs. And so I'm going to set up my ordered pairs here. This says x, excuse me, x is equal to 3 halves minus 2y. And so if I write x, my x coordinate using y's, then that means y gets to be its own name. When you write down your infinite number of solutions, you can only use one letter here. You don't get to write x stuff over here and y stuff over there, vice versa. I either have x comma stuff with x's or stuff with y's comma y. So maybe at your desk you said, well, I solved for y instead of x. And so I'm going to divide everything by 12. Then my ordered pairs, since my y looks like negative 1/2 x plus 3/4. And I solve for y in terms of x, meaning using x's to describe it, that means x gets to be its own name. Okay, whatever letter shows up in the one, the other one gets to be its own name. So you don't write me both of these. Okay, pick one or the other. And if you, well, it wouldn't hurt for you to try it, just so you believe me and so you can see that it really works. But if you use this equation instead, if you solve it for x, you should get 3 halves minus 2y. If you solve it for y, you should get y equals negative 1/2 x plus 3/4. These two lines are the same line. So it doesn't matter which equation you pick or which letter you solve for. Either give me the stuff in the left blue box or the right blue box. Don't just tell me there's infinite solutions. Tell me what they are. Okay. Hopefully that gets you started on the dependent and inconsistent.